Hello everyone, today we are going to start a lecture on semiconductors. We know the semiconductors are essential in modern life. They power our phones and computers. They are in cars and medical devices. This presentation will explore the basics of semiconductor. Since semiconductor plays a vital role in modern physics, modern world, serving as the backbone of countless technologies that we are rely on daily. In realm of computing, semiconductors from heart of microchips, which are integral of everything from personal computers to smartphones. Without semiconductor device that store, process and transit data would not function as we know them. Semiconductors enable the processing power and the connectivity that we take for granted in modern computing systems. Beyond consumer electronics, semiconductors have critical applications in other industries such as automotive and healthcare. In cars, they help manage engine systems, assist with driver safety features like airbags and automatic braking, and enable advanced technologies such as autonomous driving. In medical devices, semiconductors ensure the accuracy and reliability of tools like pacemakers, diagnostic equipments, and imaging systems, improving both treatment outcomes and patient care. So, semiconductor truly power modern world, and their continued development will be the key to the innovation of tomorrow. So, today we will explore the science behind semiconductors, exploring their material properties, how they are manufactured, and the incredible range of application they support. Today, first we'll discuss the semiconductors. What are different semiconductors? Their examples, application, properties of semiconductors, semiconductor companies, most commonly use semiconductor materials in details. So let's start. Semiconductor is nothing but the materials with conductivity between conductors and insulators, normally ranging from 10 power of minus 6 to 10 power of minus 4 ohm meter inverse. They control circuit current. They make modern electronics possible. Basically, the semiconductors are vital part of electronic device. They reduced energy consumption in circuits, and they enable smaller, more powerful electronics. So there are various types of semiconductor based on the properties and their doping percentage. It categories normally two. Semiconductor is intrinsic semiconductor, also known as pure semiconductor, extrinsic semiconductor, and impure semiconductor. Further, in impure categories, there are two types of semiconductor, p-type and n-type semiconductor. You can see here that intrinsic semiconductor, both the free electrons and holes and equal. However, in extrinsic semiconductor, it varies, depends on type of semiconductor. So there are these are the generally we see the semiconductor compounds, diodes, resistor, LEDs, etc. So before going to detail about semiconductor, we has to know about the energy bands of, uh, of the materials to differentiate semiconductor from the conductor and insulator. So why it named? Actually, the uh, the discovery of electricity, the scientists have divided the materials in three categories that depends on the conductivity: conductor, insulator and semiconductor. You know that conductors are which conduct the electricity like copper, silver, gold, aluminum, any type of metals. On the other side, insulators are those doesn't allow any electrical charge to flow through, like plastics, wood, diamond, rubber, etc. So the material which is in between the conductor and insulator, whose properties is bit different from conductor and insulator. They are not conductor, not insulator. They are in the medium, means their conductivity. So those are called as semiconductor. So very famous and well-known, well-established semiconductors are silicon, germanium, and other doped semiconductor like gallium arsenide, etc. This diversity in the conductive behavior of solid failed Bohr's model of free electrons. Instead, the energy band theory based on the wave mechanical wave was used to explain it. So in order to understand the conductivity behavior of the solid, we need to first look at the energy band theory. We will not go through the details of the energy band theory, but that just brief about energy band, that as we know a solid has various energy levels. So those levels are nothing but as called the energy bands filled with the electrons. In all this in In all these energy bands, the electrons remains bound to the nucleus and have distinct energy levels. So basically, the energy levels and band are the same. So electrons occupy the lowest energy state. Suppose these are the different energy state whose energy is, these are the lower, and this scale bar is showing the upper energy levels. So electrons normally settle into this lowest possible energy states. This follows the Pauli's exclusion principle, where no two electrons in an atom can have the same state of quantum numbers. That means in each state there will be distinct one electron with the properties. So in that particular level only one electron will be allowed, and the not every level is allowed for electrons. So here also have some energy levels. These are uh, disallowed energy states. So electrons always try to occupy the lowest energy band possible. Not every energy level is a legal state for an electron to occupy, and these legal states tends to arrange themselves in hand. So basically, these certain energy levels are forbidden for electron due to quantum mechanical restrictions. Electron can only exist in specific allowed energy states. So, why this energy bands forms? This energy in solid, basically a large number of closely paced atoms cause their discrete discrete energy levels to split into bands. So allowed energy state are we can say that allowed energy states, the regions where electron can exist, means electron will have the permission, or there will be no restriction for electron to stay there. So this we can say as it will be conduction and valence band. And disallowed energy states, those actually forbidden region where electron cannot exist. So that presence of band, we see that this is some energy state, this valence state, and above is conduction band state. That means that both place electron can stay, but in between these two, conduction band and valence band, no electron can exist. So here the band will form. So this is called the energy band gap, or energy band, or energy level, or band gap of the semiconductor. So the presence of band gap determines if a material is a conductor, semiconductor or insulator. Electron energy, as we said in previously, that electron will higher an electron energy, the closer it's get to the conduction band, where it can contribute to electrical conduction. So let us see what is the band diagram. That as mentioned, that energy gap is nothing but the difference between conduction band level and valence band level. So this is the energy band, and this type of diagram is called the band diagram. So the electrons present in the outermost energy band of an atom is called the valence electrons, and the outermost band itself is called the valence band. And above the valence band we have another band called the conduction band. The conduction band also has electrons, but these electrons are bound to the nucleus of the atom and are thus called the free electrons or conductive electrons. The electricity passes through the solids because of these free electrons present in conduction band. So there is an empty space bar. So these are basically the empty space. Here no electrons are there, and it is called the forbidden energy gap. So the arrangement of valence band and conduction band and the forbidden gap is, we can see in diagrammatically. So we can see that energy of valence band compared to conduction band is less. So this is the increasing the electron energy from valence to conduction band, and so this is the increasing voltage towards conduction band to valence band. And so if we summarize it, that this EC represent the conduction band, lowest energy state for a free electron. Valence band, highest energy state for filled outer shell, and this gap is the called the difference in energy level between conduction band and valence band is called the band gap. No electron in the band gap. So now we can from this concept of the energy band we can divide the insulator, semiconductor and the conductor. So basically the for case of insulator, this conduction band and valence gap is gap too high, above 5 electron volt. We can show those are insulated. So this region is again forbidden region, or as we define the energy band gap. So the example is like SiO2, the band gap is 9 electron volt. So it is kind of a insulator. In case of semiconductor, the gap is less than 5 electron volt. So conduction band will be here, that fill of electrons, and valence band is basically the whole. So semiconductor examples are silicon, germanium, gallium arsenide. Those band gap, silicon have band gap of 1.1 electron volt, germanium have band gap of 0.75 electron volt, gallium arsenide have 1.42 electron volt. And for case of conductor, or sometimes is also called that metal that partially filled when there is no gap between conduction and valence band, and examples are like aluminium, gold, silver, etc. So now let us move for the type of semiconductor. Scientists basically divided the semiconductor in two main types, name is intrinsic semiconductor and extrinsic semiconductor. So we'll discuss it in the following slides one by one. So first is the intrinsic semiconductor. Intrinsic semiconductor are pure form of semiconductor and barely used as they are neither good conductor nor good insulator. So let us start with the intrinsic semiconductor. This is pure form of the semiconductor. So in pure form, that we already know that silicon is the intrinsic semiconductor example. So silicon basically have the four outer shell, or we can say the fourth valence electron. You can say this is the silicon four valence electron, and these four valence electron, this is forming a stable lattice structure through covalent bonding. And if we say a complete structure form in the lattice structure to share the electron, so that silicon 4 valence electron is sharing with the neighbor electron to complete the covalent bond. So these are called the covalent bond. So silicon is a very primary semiconductor and used in very large scale integration. And you see, if we count it, the total have the silicon 14 electrons, and these are called the energy bonds or the cells of the silicon. And we already mentioned that silicon has the four outer shell and valence electron, and this outermost shell is the valence band. So at 0k, basically the highest energy band occupied by an electron is called the valence band. Okay. So now see the intrinsic semiconductor, how it's forming this energy band. And okay, so at 0k, basically the thermal energy excites some electron into the conduction band, creating the free electrons, and free electrons in the conduction band and the holes in the valence band. So however, at temperature above 0k, the thermal energy sets an electron free, and this electron, what will happen, this electron will be moved, and then it will this free electron will be now moved at above 0k temperature. But when it is at temperature 0k, that this movement will not occur, so that time it will be behave like an insulator. So what are at above 0k, what are the properties? As we say that free electrons in the conduction band can conduct the current, and holes in the valence band can act as a positive charge carriers. So first the electron and hole, this will form the paired formation, or it will create pair generation. So creation of an electron and hole pair is also known as the electron hole pair generation. Hole is simply a missing electron which leave an excessive positive charge due to extra proton. And in next step will be recombine, and this recombination is nothing but if an electron and hole comes in contact, they annihilate each other, and these electrons and holes basically is called the carriers because they are charged particles. Therefore the semiconductor can conduct electricity for temperature above 0k. At mass current at room temperature, pure silicon has only one free electron. So based on that electron and holes, this intrinsic semiconductor comes from this valence electron excitation. So based on this electron and holes, number of electron and holes in the materials, it also classified as n-type, p-type semiconductor. So will come details on this dope semiconductor. So basically this intrinsic semiconductor, here we can see that silicon have four valence electron, and these are the covalent bond neighboring silicon atoms. They are interact with each other, they are in covalent bond. But in doped semiconductor will come details in that. Basically here what happened, that if we doped from silicon have four, so if we doped higher or lower of the valence electron, the metal means materials, like if we dope the SB, that it have the five valence electron of an electron, so this SB is basically the antimony. And if we dope the boron which have the T, so here we can create a vacant place, or this is the basically void, so here we can get a hole. However, in case of antimony, here we can get a extra electron. Okay, so based on this type of doping, these p-type and n-type semiconductor forms, and we generally called this doped semiconductor. We'll come details on that. So if we look on the periodic table, that group B, group third, these are the elements, group 5A and group 6A. So basically what we are talking, the intrinsic semiconductor, pure semiconductor, those are 4A category. Here silicon you can see, and here is germanium. So this column 4 elements have 4 valence electron in the valence shell. So now if we couple together from this silicon with a partial doping, or we can say that in the material, if we add some impurity from this category, we can have the 3 electrons. This all have the 3 valence electron in the valence shell. So we can get the doped p-type semiconductor. And next, if we see that this from column 5, if we choose, then we have an option for creating that another category of the semiconductor. So now we will discuss that difference of one's doping silicon with the boron and one's doping with the phosphorus. So if we summarize that what is doping? Doping is nothing but adding impurities to silicon crystal lattice to increase the number of carriers. Add a small number of atoms to increase either a number of electrons and holes. It depends on from which column we are choosing the materials. So now let us see that this is the silicon. We know that silicon have 4 valence electron, and they are to each other. They are in the covalent bond. So now if we add the phosphorus, which have the 5 valence electron, and it so 4 will be with nearby silicon atom, they will be will form the pair, but since it have the 5 valence electron, so one extra electron that will be here, so it will be again formed next silicon next. So this, we can say that phosphorus can donate an extra electron that can freely travel around, so and leaves behind a positive charge carrier, positive charge nucleus which cannot move. Overall, the crystal still electrically neutral. So this type of material, we can say that n-type material added negative carriers. So here if we define the concentration of donor atom, we can define by Nd, concentration of donor atom, and electron is free here to move the crystal, and concentration of donor generally in this range 10 to the power 15 to 10 to the power 25 semi centimeter cube inverse, and the mobility is this range. So see that this electron is freely moving. This is from the phosphorus. So basically we see that in material they are definitely will have both positive and negative charge carrier, but we can see that majority positively charged ions we have denoted at plus, and immobile, those are immobile. Negatively charged electrons, those are mobile, and this one without circle there have one positive. Those positive charge is the minority carrier of this system. So now next move for the p type of material. So if we choose the elements from group third which have the 3 valence electrons, so let us add the boron atom which have 3 valence electron with the silicon. So this boron, since it have the 3, so it is here one side will be vacant, or here is some void. So if you want to fill, it should come from here neighbor, and again here it need to fill, it will come from near neighbor. So this leaves behind a negative charge nucleus, cannot move, and overall the crystal still electrically neutral. And So this called the p-type silicon, called the p-type, and added positive carriers. And here we can denote the concentration of acceptor as Na, and the movement of hole requires the breaking of the bond, so mobility is a bit less. And so similar, what are the similar group of other from third element we can add, and we can same structure we can get. So basically in p-type semiconductor, the majority charge carriers are whole, positively charged. Example of trivalent element used in doping process like boron, gallium, aluminium, indium, etc. The trivalent element is here is acceptor, and the semiconductor is donor. In for case of n-type semiconductor, the uh, pentavalent element is the donor and semiconductor is acceptor. So now let us see that if we join together this one p-type and n-type semiconductor, what happens and how they behave. So just imagine that one p-type n-type block and one p-type block both are sandwiched, and this is their junction. So what will happen if this side also have the majority carriers electrons and this side majority carriers holes? However, the minority carriers of electron will be present in p type, and minority carrier holes will be present in the n type semiconductor. So basically when a single semiconductor material is doped with both trivalent and pentavalent impurities, both p-type and n-type materials are create a single substrate. So junction diode is formed by placing a p-type material and an n-type in contact. So this attachment is needed for in high pressure, and it will become a single piece. So the assembly so called is PN junction or the junction diode or the crystal diode. The surface of contact of p-type and n-type, that is this, is called the junction. So the p-type region here as mentioned that majority charge carriers hold. Similarly for n-type it is the electrons. Electrons here defined in orange color, that and positive carriers are defined in plus and with the green color. So, in addition to above majority charge carriers, there are few minority charge carriers in each region. The p region contains a few electrons, while n region contains a few holes. Thus, we find that the junction there is a decrease of hole concentration from left to right, which makes the hole diffuse from p side to n side. Similarly, electron diffuse from right to left across the junction. Holes leaving an electron entering the p side makes it negative. We can see that this side become negative. Similarly, holes entering an electron leaving from n region making it positive. Thus, there will be a net negative charge on the p side and positive charge on the n side. So what will happen? This produce an electric field across this junction. As if a fictitious battery we imagine, then here we can add a battery. This side will be negative and this side will be positive. This process in electric field across the junction, as if this battery is present, while its positive terminal will be to the positive terminal will be in n side and negative terminal will be in p side. So equilibrium is established when the field becomes larger enough to stop further diffusion of the majority carriers from both the sides. The field, however, helps the minority carriers to move across the junction, and the region on either side of the junction which becomes deflected free. So this region is called the deflection region of it also, as mentioned, that this here to here, this is the deflection region, and the thickness of deflection region is varied from material to material, and is also in the range of 10 power of minus 6 meter. The potential difference across the deflection region is called the potential barrier. So we can say deflection region or the potential barrier. So this PN junction formulated on the basis of different semiconductor compounds. Very first it came as diode, transistor, integrated circuit ICs. So we'll cover all this in our upcoming lectures. So diode basically control current flow, act as one-way valves. Transistor amplifiers basically signals also used as switch, and integrated many components enable complex function. So let us see some basic semiconductor devices. So this is the two-terminal PN diode. So this is called this metal semiconductor contacts, and bipolar transistor it have PNP or also possible NPN. It have it called terminals called as emitter base collector. Bit more complex diode, that more complex semiconductor junction field effect transistor. So wherever there is a P and N, we can see that this deflection region. So it also define as source, drain, and gate. Other metal oxide semiconductor also MOSFETs. So these are various semiconductor basic devices. We will cover all this in our following lectures. So let us see that basic semiconductor, the manufacturing process, although it is very complicated and time consuming step wise, and so let us just have a idea that how it come. So the process is bit complex. It involves multiple steps. So if we summarize the major of the steps, this includes the wafer fabrication and circuit design. So it's basically silicon wafer are created. Next step, the circuit design. Circuits are designed and tested. And next is the testing. It's undergoes quality checks. All the steps are very important, and also it's a bit complex, but we are trying to step that what are the main manufacturing process steps. And last is the packaging. So now let's see that what are different application areas or industries based on the semiconductor. And so semiconductor are used in many industries: computers, car, medical devices. As we mentioned in our introduction part, many new applications are also emerging. So basically, if we categorize in these: computing, processors and memory; consumer electronics, that smartphones and appliances including household all appliance electronics; automotives, that engine control and safety systems; and also most importantly healthcare, imaging, and also in the patient. So if we look about the what is the global market of global semiconductor market, so I have just given this for a brief idea from 2020. The semiconductor market is growing, and demand is and also driven with the artificial intelligence and ITO. So this is basically the that we can see from the graph. It is monotonically increasing, and the oath to meant that Asia Pacific is the largest market. Semiconductor revenue has grown significantly, driven by increasing demand and innovations. So this all about the semiconductor types, materials, um, their manufacturing process and global market. Let us see that who are the major players in semiconductor industry. So the industry is dominated by a few key players, including Intel, Samsung, TSMC lead the market basically. They invest heavily in research and development. So Intel leading processor manufacturer, Samsung major memory and chip suppliers, the world largest foundry from TSMC. So, however, there have several benefit, advantage, and same time it also has various challenges. Industry face many challenges. This includes high cost and supply chain issues. So, future innovation includes new materials and designs, in particular the cost, supply chain. If we point out that first will be the cost, second is the supply chain, and third is the putting physical limit. So the future innovation is that uh, include new materials and design. So let us conclude with the continued importance of semiconductors. So semiconductors will remain crucial. They are vital for technology and innovation. Investing semiconductor is very important. So if we see that innovation, growth, and importance are simultaneously needed. The semiconductor enables technological advancement. The continued growth and innovation in semiconductor tech are essential. So let us conclude. That's all for today. I hope it will find helpful. Thank you. Thank you very much.